In the previous video, we talked about the backpropagation algorithm. To a lot of people seeing it for the first time, the first impression is often that, wow, this is a really complicated algorithm and there are all these different steps and I'm not quite sure how they fit together, and it's like kind of a black box with all these complicated steps. In case that's how you're feeling about backpropagation, that's actually okay. Backpropagation, maybe unfortunately, is a less mathematically clean or less mathematically simple algorithm compared to linear regression or logistic regression. And I've actually used backpropagation, pretty successfully for many years, and even today I still don't sometimes feel like I have a very good sense of just what it's doing, or sort of intuition about what backpropagation is doing. If for those of you that are doing the programming exercises, that will at least mechanically step you through the different steps of how to implement backprop, so you'll be able to get it to work for yourself. And what I want to do in this video is look a little bit more at the mechanical steps of backpropagation and try to give you a little more intuition about what the mechanical steps of backprop is doing, to hopefully convince you that it's at least a reasonable algorithm. In case, even after this video, in case backpropagation still seems very black box and kind of like too many complicated steps and a little bit magical to you, that's actually okay. And even though I've used backprop for many years, sometimes it's a difficult algorithm to understand. But hopefully this video will help a little bit. In order to better understand backpropagation, let's take another closer look at what forward propagation is doing. Here's the neural network with two input units, that is not counting the bias unit, and two hidden units in this layer, and two hidden units in the next layer, and then finally one output unit. And again, these counts 2, 2, 2 are not counting these bias units on top. In order to illustrate forward propagation, I'm going to draw this network a little bit differently. And in particular, I'm going to draw this neural network with the nodes drawn as these very fat ellipses so that I can write text in them. When performing forward propagation, we might have some particular example, say some example xi comma yi, and it will be this xi then we feed into the input layer. So this is maybe xi1 and xi2 are the values we set the input layer to. And when we forward propagate it to the first hidden layer here, what we do is compute z21 and z22. So these are the weighted sum of inputs of the input units. And then we apply the sigmoid or the logistic function, and the sigmoid activation function applied to the z value gives us these activation values. So that gives us A21 and A22. And then we forward propagate again to get, here Z31, apply the sigmoid or the logistic function, the activation function to that to get A31, and similarly like so, until we get Z41, apply the activation function. This gives us A41, which is the final output value of the neural network. Let's erase this arrow to give myself some more space. And if you look at what this computation really is doing, focusing on this hidden unit, let's say, we have that this weight, shown in magenta there, is my weight theta 210. The indexing is that important. And this weight here, which I guess I'm highlighting in red, that is theta 211, and this weight here, which I'm drawing in green in cyan, is theta 212. So the way we compute this value z31 is as equal to this magenta weight times this value, so that's theta 210 times 1, and then plus this red weight times this value, so that's theta 211 times A21, and finally this cyan weight times this value, which is therefore plus theta 212 times A21. And so that's forward propagation. And it turns out that, as we'll see later in this video, what backpropagation is doing a process very similar to this, except that instead of the computations flowing from the left to the right of this network, the computations instead flow from the right to the left of the network, and using a very similar computation as this. And I'll say in 2 slides exactly what I mean by that. To better understand what backpropagation is doing, let's look at the cost function. Here's the cost function that we had for when we have only one output unit. If we have more than one output unit, we used to have a summation, over the output units indexed by k there. But if you have only one output unit, then this is a cost function. And we do forward propagation and back propagation on one example at a time. So let's just focus on a single example, xi, yi, and focus on the case of having one output unit. So yi here is just a real number. And let's ignore regularization, so lambda equals 0, and this final term, that regularization term, goes away. Now, if you look inside this summation, you find that the cost term associated with the ith training example, that is the cost associated with training example xi, yi, that's going to be given by this expression, that the cost of training example I is written as follows. And what this cost function does is it plays a role similar to the squared error. So rather than looking at this complicated expression, if you want, you can think of cost of I being approximately, the square difference between what the neural network outputs versus what was the actual value. Just as in logistic regression, we actually prefer to use the slightly more complicated cost function using the log, but for the purpose of intuition, feel free to think of the cost function as being the sort of squared error cost function. And so this cost of I measures how well is the network doing on correctly predicting example I. How close is the output to the actual observed label yi. Now let's look at what backpropagation is doing. One useful intuition is that backpropagation is computing these delta superscript L subscript J terms, and we can think of these as the quote error of the activation value that we got for unit J in the elf layer. More formally, and this is maybe only for those of you that are familiar with calculus, more formally, what the delta terms actually are is this: they're the partial derivative with respect to zlj, that is this weighted sum of inputs that we're computing, these z terms, partial derivative with respect to these things of the cost function. So concretely, the cost function is a function of the label y and of the value, this h of x, output by a neural network. And if we could go inside the neural network and just change those zlj values a little bit, then that will affect these values that the neural network is outputting, and so that will end up changing the cost function. And again, really, this is only for those of you that are expert in calculus. If you're comfortable with partial derivatives, what these delta terms are is they turn out to be the partial derivative of the cost function with respect to these intermediate terms that we're computing. And so they're a measure of how much would we like to change the neural network's weights in order to affect these intermediate values of the computation, so as to affect the final output of the neural network h of x, and therefore affect the overall cost. In case this last part of this partial derivative intuition, in case that didn't make sense, don't worry about it. The rest of this we can do without really talking about partial derivatives. But let's look in more detail about what backpropagation is doing. For the output layer, it first sets this delta term, let's say delta 4,1, as yi, if we're doing forward propagation and back propagation on this training example I. It says this yi minus a41. So this is really the error, right? It's the difference between the actual value of y minus what was the value predicted. And so we're going to compute delta 41 like so. Next, we're going to propagate these values backwards. I explained this in a second, and end up computing the delta terms of the previous layer. We're going to end up with delta 3,1, delta 3,2, and then we're going to propagate this further backward and end up computing delta 2,1 and delta 2,2. Now, the backpropagation calculation is a lot like running the forward propagation algorithm, but doing it backwards. So here's what I mean. Let's look at how we end up with this value of delta 2,2. So we have delta 2,2. And similar to forward propagation, let me label a couple of the weights. So this weight, which I'm going to draw in cyan, let's say that weight is theta 2 of 1, 2. And this weight down here, let me highlight this in red, that's going to be, let's say, theta 2 of 2, 2. So if we look at how delta 2, 2 is computed, how it's computed for this node, it turns out that what we're going to do is we're going to take this value and multiply it by this weight and add it to this value multiplied by that weight. So it's really a weighted sum of these delta values weighted by the corresponding edge strength. So concretely, let me fill this in. This delta 2, 2 is going to be equal to theta 2, 1, 2, which is that magenta weight, times delta 3, 1, plus, and then the thing I had in red, that's theta 2, 2, 2 times delta 3, 2. So it's really literally this red weight times this value plus this magenta weight times this value, and that's how we wind up with that value of delta. And just as another example, let's look at this value. How do we get that value? Well, it's a similar process. If this weight, which I'm going to highlight in green, if this weight is equal to, say, delta 312, then we have that delta 32 is going to be equal to that green weight, theta 312 times delta 41. And by the way, so far I've been writing the delta values only for the hidden units but excluding the biased units. Depending on how you define the backpropagation algorithm, or depending on how you implement it, you may end up implementing something to compute delta values for these biased units as well. The bias units always output the value of +1, and they are just what they are, and there's no way for us to change the value. And so depending on your implementation of backprop, the way I usually implement it, I do end up computing these delta values, but we just discard them and we don't use them because they don't end up being part of the calculation needed to compute the derivatives. So hopefully that gives you a little better intuition about what backpropagation is doing. In case a lot of this still seems somewhat magical and somewhat black box, in a later video, in the putting it together video, I'll try to give a little bit more intuition about what backpropagation is doing. But unfortunately, this is a difficult algorithm to try to visualize and understand what it's really doing. But fortunately, I guess many people have been using it very successfully for many years. And if you implement the algorithm, you can have a very effective learning algorithm, even though the inner workings of exactly how it works can be harder to visualize.